Welcome back. In this video, I'm going to talk about some strategies to help guide us in the process of specifying a spring for a particular application. So as I mentioned previously, you're probably not going to design your own unique spring. For most situations, it's much easier to simply buy a spring from a catalog. So what we're going to look at today is the things that drive how we pick the spring that we will use in a particular application. So what we're going to have are both design variables and constraints. So design variables are things that we have choices in, and constraints, of course, are the things that constrain the problem to a searchable region. So things that we're going to be able to have some choice about and have to end up making choices in order to find a spring that we want. Of course, it's going to be the material that the spring is made out of. That's going to define a lot of the yielding and fatigue properties that we're going to care about. There's the length, as well as the lurking length, the solid length, basically all the different lengths that we care about for the particular design. We're going to have to make decisions about the end conditions. Going to have to make decisions about the sizing. That is the mean diameter, the wire diameter. We're going to have to make decisions about the surface finish. So that is whether it is peened or unpeened. And we'll talk about that a little bit later. And we're going to want to look at basically choices that we're going to make in terms of the working range. So choices for percentage for the force minimum, as well as whatever crash allowance we want. So there are a lot of variables here and things that can change. And of course, we're going to have constraints in almost any real problem. There is, what's available, what is possible to manufacture. Not all things are manufacturable. That's why we talked about a range of spring indexes that are possible to make. So even though you can run these calculations with any number you want to plug in there, not every number is actually realistic. In most contexts, there's actually going to be some limits on the space available for where we put the spring. So for example, if we are insetting this spring inside a container, we have dimension limits. So that might be an outside diameter if we put this thing inside a container or a hole, or it might have an inside diameter if, for example, we put the spring on a rod. So those might be constraints to our problem. And there can be many other constraints too in terms of the amount of life we want to get out of this, the amount of free range of motion that we need. And if we look at this problem and we have a whole set of constraints and a whole set of potential design variables, the space of possibilities is huge and can be a little overwhelming to look at without any sort of guiding principles to go off of. So the point of this video then is to give you some designing guiding principles to go off of. So let's talk about this design process. For speccing out a spring. So a couple steps are, first of all, we want to make sure that our spring is not going to go solid. So as best as we can, we want to avoid going solid by instituting a crash allowance. And we'll walk through what this process looks like in just a little bit. Second step, we want to make sure that if the spring did go solid, that the yield point is after that. So the yield point is after the force that would make it go solid. That means basically it will never yield as a result of the forces that we put on it. And third is specific to the type of springs that we're dealing with. So we're going to be concerned about stability. We want to make sure that we avoid buckling. And we want to make sure if we are using the spring in a pretty rapid context that we avoid any of the natural frequencies. Right. And so there's going to be quite a few steps in here that we'll go through, and if we avoid having the spring buckle and we avoid its natural frequency, we know it's not going to yield. The last part will be basically designed for whatever life that we want to get out of the spring. So not every spring needs to have an infinite life. And so if you want a particular life out of your spring, then we can use our failure criterions and work backwards to what type of life, what types of stresses, what type of materials we need to do that. So more than likely, this is the type of thing that you'll set up in an Excel document for a particular problem and explore some options. And there's some nice worked out examples showing how we set up constraints and design variables and explore the options within there. So let's talk about this process a little bit. So for example, number one here was allowing some crash allowance. So how do we do that? Let me say crash allowance. So if we are doing a first pass design here, we might give a crash allowance of, say, 10%. So if we want, that basically means that the maximum force that we put this thing on will be, it'll take 10% more to get to the deflection. So the deflection that makes it solid minus the deflection of the max should be probably greater than, say, about 10% of the maximum deflection. All right, so this is just a general guide. As a design rule, you can do less and you risk that shock load. You can do more and it means you're paying for more spring than you're using. So that's a design choice that you have to make as an engineer and decide what's right in your particular context. So how would we figure that out? Well, we can figure out the force that takes to go solid, right, would just be the spring rate, whatever it is, times the deflection to go solid. So what is the deflection to make it go solid? Well, that's going to be the resting length minus the length when it's solid. Well, how do you know how big it is when it's solid? Well, that's a geometry factor, right? We just know that if we add up all of the wire diameters together times the total number of coils, that's going to be the same as the solid length. So if there are, 5 coils here, 1, 2, 3, 4, 5, and each coil has a wire diameter of D, then the total solid length when all the rings are pressed up against each other with no spaces left is just going to be the wire diameter times the total number of coils. So that allows us then to find a force that makes it go solid, and then we can reduce that to come up with a force that will be our absolute maximum. So that's the maximum force. Now, of course, we could work this problem backwards, right, and say, I know I'm operating between this force and this force. You can work it the other direction and say, all right, what's 10% more times the spring rate to find the total force that we want, the force that would make it go solid. And that gets us back to this default length. So either start with the default length and find the F max, or start with some F max and find a resting length. All right, so next was to find a to make sure that the spring will not yield before it goes solid. So what we can do then is take the maximum shear stress. We remember from our equations before, Berg-Strausser factor times 8 times force, mean diameter over pi d cubed, and make sure that is less than the yield strength and shear divided by n, whatever factor of safety you want to keep it below. So what force would this be? This would be the force that makes it go solid. So typical factors of safety for springs against yielding is often 1.3, 1.4, something like that. It doesn't have to be real high. So how do we know the yield strength for these different materials? Well, we have tables for that. So the elastic limit in either shear, in tension, or torsion is typically a percentage of the ultimate strength, some percentage of the ultimate strength. And we have a table 10.5 in the Shigley book, which has all of those percentages for different types of wires and diameters that are out there for commonly available springs, metal springs. And when we calculate the ultimate strength of these materials, it's based on a variable a over the wire diameter raised to the m, where a and m are variables that we also find from a table. So this table is 10.4. The process of doing this actually involves quite a bit of table work, but we can find the specific yield strength as a percentage of the ultimate strength from 10.5 and the ultimate strength for different wire materials from 10.4. All right, so if we make sure that our yield strength at solid, if we make sure that the stress due to the force at solid is still less than the force it would take it to yield with our factor of whatever factor of safety we want, then we're confident that the only thing that can happen to us are the remaining three things that we're concerned about: buckling, natural frequencies, which is quite a bit more rare, and the particular life that we want. So let's then talk about avoiding buckling. And natural frequencies. So this one's a pretty straightforward process, exactly what we had before. You just have to make sure that resting length is smaller than the Euler factors that we talked about last video. So 2 times E minus G over 2G plus E to the 1/2. We saw that before, and what the A alpha factors are between 1/2 and 2. So that makes sure we are stable, and to make sure that we avoid the natural frequencies, we want to make sure that the frequency that we vibrate our spring at avoids any of the natural frequencies. So if we vibrate a spring at the material's natural frequency, it's going to induce harmonic vibration, which, if you remember from your dynamics class or your control theories class, that's going to be a bad thing. So what we want is a frequency. Experimentally, it's been shown that you want to avoid if you have both ends constantly in contact with the surface, which again, as a design principle, we always keep a minimum amount of force on a compression spring. So it's always got two surfaces in contact. So if that is true, then the frequency that we want is 1/4 times the spring rate K times gravity G and the weight of the spring. So K is the spring rate, G is gravity, is the force of gravity, and W is the natural the weight. Of the spring. And of course you can figure out the weight of the spring based on the density of the material and multiplied by geometry, or you can just put it on a scale and actually measure the weight. Of course, a manufacturer will tell you the weight of their spring as well. They can do that. So now the natural frequency is generally not something that we get close to too many times. However, we can figure out this frequency is the first harmonic. The second harmonic will be the multiple of that. So the first one it'll fail the first time we get to the first one. So as long as we don't ever get to the first one, we'll never get to any of the higher ones because it won't be going any faster than that. So as a general principle, the frequency of operation needs to be about 15 to 20 times smaller than the frequency that will get you to your natural frequency, where it's going to induce those extreme vibrations. All right, so those are just two things that are quick checks to completely throw out any bad alternatives, because obviously any design choice that allows for buckling or allows the natural frequency will be completely unacceptable. The last part was actually designing for the life that we want to get out of it. So as we said, as we've checked in step 2, if we rule out yielding because we put the yield point after it goes solid, so after it goes solid, now we're talking more like it's the material itself, like a tube yielding, then the only thing now we have to worry about is fatigue failure. So here's where we get to apply those failure theories that we learned before. So a fatigue life loading on a spring, an extension spring is going to be constantly in tension, where a compression spring is going to always have some mean stress, I should say torque, or shear stress, some mean shear stress that is in compression for a compression spring and extension for an extension spring, or tension. So the amplitude of that shear stress, of course, is going to be the same thing as 8 times the amplitude of the force that we're putting into it times the mean coil diameter and pi d cubed. And the mean shear stress, of course, will be, sorry, don't forget the Bergstrausser in there, the kb factor 8 times the mean force that we put into it, and pi d cubed. And we'll find the same way, the amplitude force is going to be max minus min over 2 and of course the absolute value of that, and the mean is just the mean average stress, max plus min over 2. All right, so that gets us one part of our equations. And you'll recall now that we're in a pure shear case, right? So we can use the shear expressions. So the ultimate strength in shear is about 67% of the ultimate strength in tension. And the last part then would be the endurance strength. And as you recall, we talked about lots of Marin factors to change some hypothetical endurance strength to some actual endurance strength to fit our situation. If you think about that a little bit, you go, wow, this could be a really complicated problem because there's geometry with the spring, there's the diameters of the wires change, the loading is in shear. What should these Marin factors be? Well, interestingly, experimental results show that those things don't matter. The only thing that matters is the material it's made out of and whether it's peened or unpeened. So for steel springs, the endurance strength is either 45 kpsi, which is about 310 megapascals, or it is about 67.5 kpsi, also 465 megapascals. And this depends on whether it's peened or unpeened. So peening is an extra manufacturing step, and effectively what it is they're put in a tube with lots of tiny little hard metal balls that strike and hit and induce surface hardening on the outside of the spring. So that's an extra additional manufacturing step, so as you can guess, it's generally going to increase the cost of a spring. Slightly, but not a huge amount. So we just need to decide as one of the design variables whether we're talking about a peened or unpeened surface. And then, of course, we can just look at whatever Goodman equation for fatigue life. We can set tau A over the endurance strength and tau M over the ultimate strength and shear, and decide if we want to have infinite life with a Goodman equation with a Goodman factor of safety greater than 1, or we can use the finite life approach and estimate for the number of thousands of cycles. So there's lots of situations where we don't need infinite life out of a spring. If it's the lock mechanism inside a door, we're probably not going to unlock and lock a door 1,000,000 times within the life of that door. 1,000,000 is a pretty big number. On the other hand, in automotive applications, the valve spring has to open and close that valve many millions of times within the life of that valve service where the spring might be replaced. So it all depends on our application of whether we want finite life or infinite life, and we can use the same finite life equations we had before. All right, so that doesn't really tell us exactly what variables to pick for things, but instead what it does is it gives us a set of limiting constraints. So if you imagine a multi-dimensional graph here, which I obviously can't draw in 2D, but there are many potential variables, and what we are going to be doing is trying to find the space of good designs. That is, what are the springs that will work for us and give us the performance that we want in terms of the working range, the forces that go into it, the cost, the life that we expect out of it, and what we want to then rule out is anything that's going to cause yielding or early fatigue failure, natural frequency stuff, and stability issues. So our goal and our intent is to calculate all of these things in a systematic way, such as in a spreadsheet, and then make sure that anything else fits within what could be a good design. And then we're going to need some alternative evaluation variables to come up with what is an equivalent, what is a good metric for this design, such as relative cost of the materials. All right, so next time we'll work on a couple different examples, and that'll be it.